So in this problem, we're asked to find the velocity of water flowing out of the nozzle of a fire hose. Now, one of the pieces of information we're given is R, which is the rate of flow of water through the fire hose. And that's going to be delta V over delta T. Now we're going to draw a diagram very similar to what we drew for the raindrop problem, except this time it's going to be a tube of water that's expelled from the fire hose. So what we're really looking for is V, the velocity of the water. And the length of this tube is actually going to be V delta T, because the water is moving at velocity V, which means it covers that distance in a time delta T. So that's the amount of water that will leave the fire hose in that time. And it's going to have cross-sectional area A equals pi r squared, where r is the radius as the water leaves the tube. So that's going to be the radius of the nozzle itself. As it turns out, although we're given the diameter of the fire hose, that's not actually important for the problem. So this gives us delta V equals little v delta T times pi r squared. Rearranging this and dividing by delta T, we can get V equals r over pi r squared. Now plugging stuff in, we're given that R equals 250 gallons per minute over pi, and we're actually given the diameter of the nozzle rather than the radius. So the diameter is 9/8 of an inch, or 1 1/8 of an inch. So dividing by 2 to get the radius, we get 9/16 of an inch, and then we square that. And if you do the calculations and do a little bit of estimation, this turns out to be approximately 25 meters per second. Now we're also asked to find that the force, if this water is to hit a wall, stop, lose all velocity, and just sort of dribble down the wall. And the way we're going to do this is actually using the fact that if the water is exerting force on the wall, then the wall must also be exerting the same force back against the water. And this is going to be useful because we know that force causes a change in momentum. So this tube of water is going to have some momentum P. As it hits the wall, it's going to have to lose all of that momentum in order to come to a full stop. So since force is constant, that's going to be delta P over delta T. So all we need to do is find the full momentum of an entire tube of water over some time delta T, and that's going to give us the force. So remember, momentum is just mass times velocity, so this gives us mv over delta T, where this is mv for this entire tube, which we're treating as one object, and m is just going to be rho times v. So that's going to be rho times big V, which is the volume of that entire tube, times v over delta T. And notice here we have V, the volume of that tube, divided by delta T, and that is just the rate of flow R from back there. So here we can get F equals rho times R times little v, the velocity of the water, and then we can plug in known values, 1.0 grams per centimeter cubed. R we were given to be 250 gallons per minute, and our estimation for V, 25 meters per second. Now we can do all of this math, do a little bit of unit conversion, and this comes out to be approximately 390 newtons.